Was very happy to be invited here, and I'm glad that there are some people in the audience, very few, but more I see more online. So I'm excited to be here. So I'm from Teacher College, Columbia University, and I'm visiting Hong Kong. I love Hong Kong, by the way. It's beautiful. I've been here since last Thursday, and I'm going back tomorrow. So this is my final people that I see in Hong Kong, which is very exciting. So you probably look at this title and you say, what is this? This is a long title: infect, attach, bounce off. What is it going on? What is mechanistic reasoning and canonical understanding? There's a lot of unfamiliar words here, but I promise you, look at it very closely, because I'm going to ask you some question at the end, see if you got it. I hope you will. So this is so I'm from Columbia University, and the Transformative Learning Technology Lab is the lab that Professor Blickstein is leading, and I'm working with him. And the lab is a place where we're trying to radically change how children learn STEM, which everybody wants to do. But I think the most interesting thing that we do is we combine research and practice. So it's not just like rewriting papers and thinking about theory. We're actually implementing a lot of the stuff at schools, very in real school environment, in real system. And I think that's why I love it so much, because I feel like if you connect to schools, you can really make a difference, and you can impact education, not just sit in the environment of the university and talk about the school, but actually do things in the school. So I really appreciate that. And this is I had to show you this. Do you know this graph before? Have you somebody seen that graph before? So this is a beautiful graph. I love it. It's made by some company that is doing large statistic in the US. And the idea here is you look at, will your job be automated tomorrow? And it's very, very relevant to what we're doing now, you know, with the ChatGPT and all the AI scare that we have. And we talked about it in CITE last week in the CITERS conference. But the idea, if you look carefully, you look at the left on this side, you see the least likely to be automated workforce or role, and on the other side, the most likely to be automated. So you can see that waiters and retail sales and personal care aides and truck drivers will be most likely to be automated. And you know, I'm living in the Bay Area in San Francisco, and I all the time see cars with no driver. And it's kind of scary at the beginning, but you see a regular car with everything. I took pictures, like a ghost car, and you can use them as Uber, the taxi. So it's happening. It's not. And this graph was made in 2017. I showed it the first time in 2017, and it's so real. But look at the teachers. Teachers are still here. So I wanted to show you this because I think we have to change something in education. And we need some skills and practices that are different, because those a lot of things are not really relevant anymore, right? What do we want to teach kids? What do we want to do it? So I think there is this, I call it this, how do we teach STEM? How do we teach science for a world that does not exist? Yes, there is a lot of uncertainty, a lot of things. Like, I have 3 kids myself, and like asking me, what should I learn? I don't know. There's a lot of uncertainty. Just learn something. You need to learn. That's what I know, right? But you don't know exactly what. So we're doing a lot of project, and it was really hard for me to decide what project I'm going to show you and what do I do. And I know Nancy was asking something, and I was saying, maybe I don't show you. Should I show it? Not show it? We're doing work. So we're doing a lot of stuff, and these are just pictures. It doesn't say anything to you, but you know, I see one, and I can talk for 3 hours on each one of those projects. Those are the projects that I'm leading in the lab. You can see there is one ISF, which is, you notice it's the Chinese, this international school in Cyberport that I was just being there all week, and they hosted me wonderfully. But I'm going to talk about one project that I feel very near, maybe close to my heart, because I'm a PI there and I like the work and I feel it's interesting. I hope it's going to be interesting for you, but if you find it's a less interesting, you can ask me again, because there's more project to show. Hey, Renato, come sit here. Yeah. This is Renato, by the way, a PhD student Paulo's lab, Professor Blickstein lab at Columbia University.
Yeah.
Oh, we have some people zooming in, so
Nice.
yeah.
So Zoom thing?
I think we have some people doing this. It's okay. Yeah, but it's here. You can say hi. So hi, Renato. Okay, so the project that I'm going to talk about it, and I don't want to have a lot of time, so I have to rush, is called MoDa, modeling and data. Is the main idea is how computational modeling can be made a sustainable practice across middle school classrooms through design and research. And the project has two paths, design and research. And I'm going to show you both, just so you'll know what is the project about. So I'm going to talk about the project vision and design, then I'm going to talk about the research, and then you can try out MoDa or not, or I can send it to you or walk you through whatever you would like to do. Okay, and hopefully it will work, and I'm not going to breeze next to this thing that is almost, yeah. Okay, so the vision. So the project was started, it's a 3 years project, National Science Foundation for DRK-12 that we received 2 years ago. It investigates how computational modeling can be a sustainable practice. And here you could see many of the people who are involved in this. You can see Professor Blickstein and some people from MIT and UC Berkeley. So we have a very large group that works on this. And that's what that's why it's so excited, because I love to collaborate, and there's a lot of collaboration under this project. And the motivation to start this project was, it started with the idea that scientific modeling is a very powerful tool, but also it's very, I don't know if you know, but very hard to enact in classroom computational modeling. And yesterday I was in one of the schools without name, and I was asking who's doing computational modeling in the science classroom, and nobody raised their hands. So it's really hard to do. And it's a very important skills and practices. You know, we talked about AI and how things are going to disappear. Some roles are going to disappear, some job not going to be, or maybe this is a job that needs to be there. So models are used in classroom to usually, if you do modeling in the classroom, you bring ready-made computer modeling, you bring it to the classroom, and it's kind of confirming theory that somebody already explained to others. And you don't explore ideas, but you just like look at it, manipulate, maybe move a little bit, slide, see what's going on. You're not designing your own model. And if you are using something to design your own model, it's usually a programming language. Sometimes it's very hard to put it in the classroom. It's challenging for novice. You know, teachers, when they see this and they need to teach science too, they say, I want to focus on science. I can't have computer modeling programming in the science classroom. It's too much. And it's required a lot, both from teachers and from the teachers. Sometimes they don't have time. It's very time consuming. So it's very hard to use as part of classroom. And we've been in the classroom, as I said, we are in the classroom. We saw it's a big issue. It's needs, right? Another thing is that when you are scientists, and some of you are scientists, you know that you do an experiment in the lab and you design a model based on data. You look at the data, you design the model, you validate the model based on the data. In the classroom, mostly it's the student used model very disconnected from the experiment and data. Remember, you were doing science in the classroom? I don't know. But if you do, you go to the lab, you have instruction. Usually it's like a cake recipe. You do put everything inside. And then in another day, in another time, in another parallel area, you go to the classroom and you are doing computer modeling, which is very disconnected for what you did in the lab. Hello. So that's what we decided to do, what we're doing. And also we have a lot of theoretical background. I'm not going to go through it, but we based all of our work on a very heavy theoretical background. We looking at 3 different theoretical backgrounds. One of them is domain-specific agent-based modeling, which we have a few people in our group that wrote those papers, and then integrating data in modeling. It's our group that did the papers, and then extended engagement in modeling and data. So we have this background of theoretical. And so this is the web-based tool we designed. So we designed this build. I don't know if any of you know Scratch. So it's kind of the modeling scientific Scratch. We want it to be, that's the vision, it have this a scientific modeling Scratch for designing science experiment. So the idea is that we call it MoDa because it's modeling and data. You can see that on the left side, there is a coding workspace. That's where you drag and drop all the coding. There is a simulation workspace and a real world data. And there's different data. It depends what you want to teach. And also there is one data visualization. We have a company that designed this with us, but we are doing all the analysis, all the design feature and design principle. So actually we have a lot of design principle that leading us to design something good. And that's based on the theory and all this. So one of them is block-based modeling. We're thinking about blocks, but when we want it to be accessible to students, domain-specific modeling, meaning that it doesn't have all the blocks in the world. Scratch has tons of blocks. This has a very specific, limited number of blocks that connected to the topic that we want to teach. So for example, we teach about diffusion of ink in water. We have blocks that connected to ink diffusion in water. We don't have other blocks. There's also, maybe I can show you. So these are the 6 principles, but I can share with you. Maybe it will be easier to share with you. This is the environment. Do you see it? Yeah. So we have 3 buckets, and these are the blocks. So you can see there's not too many blocks. There's some general blocks, some property blocks, some action blocks, some control blocks. And let's say I want to create water particle. So I'm just dragging it up. Okay, I want a lot of them, a lot of particle. And now I want to ask the water particle to move. Okay, so I'm just dragging the move here. And I can do that. Maybe I can click here and I play and see what happens. So you see the molecule are moving. I don't know if you see it from there. Do you see it? So they're moving and they're disappearing. Okay, why they're disappearing? Because I didn't know what to do and I didn't put anything that they go. So they go, they do exactly what I told them to do, move, they go. So if I want to do something, I have to put something and tell them maybe to interact or maybe to attach or maybe do something else. And if I add that, look what they're doing now. Okay, so one principle was to look at the domain specific, so very limited amount of blocks. There is another one we called unpacking, and the idea is to let the student do complex things, not just simple, so they can go to complex programming. And you click at this plus, you can see what the computer programmer was thinking when he did create water particle. So their speed, their position, their heading, there is the mass of the particle, and so forth. And we have a few of those, so they could do that. We also always have the data, and I'll show you what type of data do we have here. This is specifically an experiment in the house of ink and water, hot and cold water. You can change it for hot and cold water, and the visualization is here. Let's go back to the... So this is the idea of the 6 principles. I hope I went through all of them. This is the unpacking, move from simple, progressively complex model. I show you that. This is the linking data and modeling. We started the project and we already have 3 complete curriculum with 3 different topics. For each one, we have very specific data. And we have one for ink spread, which is examples of student experiment, real experiment. We have something about smoke spread. So we have satellite data, just for satellite data of smoke spread. This one, I think, it's somewhere in California. There was a whole fire. I don't know if you heard about it, but that's the data from there. And here is another one that we're doing about conduction of heat transfer in different material, metal and wood and glass. And we are using a sensor from Goggleboard, sensor from a microcontroller. So we have real data from sensor of microcontroller. So we have, you can see you have 3 types of data right here. We're looking at ink data, we're looking at smoke data and conduction, but all different types. So now we have other units that are kind of on the process. We have something about photosynthesis. We have something about virus spread. So we have CDC data about the virus, about the COVID. And so we are working on more and more projects, and students are designing it for this purpose. So this is a thematic unit. We started with the idea that we want to do something that is around the movement from high to low concentration and the impact of temperature. So this one, those are the three that we started with them. So you want to ask something?
Experiments of real diffusion.
Yes, yes.
Then they need to use Flash to represent it and replicate without what the answers.
Exactly, but not just that, they need to explain. They do exactly what scientists do. Our scientists, that's what they do. They find a phenomena, they look for this, and they're very excited trying to explain this. How do you explain it?
So what's a prompt for the students?
I'll share with you.
Would you mind going back to the model working in the comparison with the video? Because I think that's a kind of
Interesting.
part. Yeah.
This
What
one.
does that mean? Like having put the glass in the ink
Yeah, so you can,
model.
right, you can see it always side by side. You can explain by putting those blocks to explain what is happening in terms of molecules and particles, and you can look at the data and validate it. So for example, if student is making a mistake, and I'll show you this in a minute when I start showing you the research part, I'm just showing the design, you will see that actually the comparison with the data makes them realize how to explain how to come up with the right explanation. We don't want to tell the student, how does diffusion happen? We want them to come up with the right explanation by themselves, thinking about this and trying different things. The idea is to make them think and use the computational modeling as a way to think, as a tool to think with. That's how I see it. So there's a lot, it's not easy for teachers because they don't tell the kids the exactly answer. They don't explain yet what it is. They let them play with it and find how to do it, how to explain the phenomena. So I think that's what the beauty of it, but I know that it's very complex, and I will tell you what we do with the teachers and how it works. I think one of the things that because we worked very close with teachers, and maybe I didn't say it because I didn't get there, but I think it's the next slide. We have a co-design, that's what Nancy and Professor Law was saying. We have a very strong co-design process with teachers. We meet them every month for 2 hours, sometimes Zoom, sometimes not Zoom, and talk about this, how to implement this in the classroom. So we have monthly design sessions since October 20. We have 6 teachers that stay with us, which is very, very exciting. We also do co-planning session to plan the next unit. So they help us think about what are the units that they want to teach. And we also had some co-design session in the summer. So we had this like group thinking in the summer and working with them. So I really appreciate them very much. It's a part of the work and they're like excellent. And then also they were very interesting in doing things for them, and they wanted to make it work in the classroom. So they asked them to do a dashboard for the teacher. And if you see, this is a teacher see a view of all the project that is happening in the classroom in their computer. So he see those blocks and he could say, you know what, this student, who did this one? Come explain what's going on. How do you explain diffusion? Can you show everyone? And it really helps because then they have a share outs. They have a conversation around it. It's working. Okay, so this is the design. This is the tool, and you're all welcome to try it. And I want to show the research because I'm very excited about the result, and I want you to be excited as well. Thank you, Renata, for taking some pictures. Okay, so first, I'm very proud because we've been writing all the time. There's a lot of research going on. And all of us are like writing machine, and we do a lot of conference paper and we do a lot of papers. And we actually, if you look at my screen, you'll see a paper in the writing right now. I'm going to show you for a second, this one. But we're writing all the time. And this is very interesting. We have 6 teachers. We have 46 hours. I think it's 460 of hours. And we have 400 of students. And the project that I'm going to talk about, because I was talking about it all the time, I'm going to not teach you something new, but look at how does ink spread in hot and cold water? It feels like very simple question, right? How does it happen? It's easy, right? But it's actually a very core science concept in both biology and chemistry. And as a background in biochemistry, I really feel very connected to diffusion. So I'm going to talk about this and what happened in the classroom. So I will talk about what happened in the classroom with data. What are the data resources? So in the classroom, the teacher is going inside. Usually it's about 8 days of work. It could be more than 8 days, but this is what we did in 8 days because this teacher allowed us to be in her classroom for 8 days. So we took what we got. We could do it more. Between 45 minutes in a session to 60, depends on the teacher. We start with essential oil. She opened an essential oil and she said, do you see something? Do you smell something? What do you smell? And raise your hand if you smell something. And all of a sudden, all of them like this. At the end of the classroom, somebody, oh, I smell something, but it takes a while. So what is going on? So what is this phenomenon called? And they're very excited. There is a smell of lavender in the classroom. I wish I brought it here, so I will do it with you, but maybe next time. And then they go to the classroom and they do a lab. You don't need a lab. You can do it in the classroom. They actually do it. You were asking about this. So you take 2 cups of hot and cold water with ink, and they check after 2 minutes and they see what is faster. How does it work? What is faster, cold or hot water? Some of them at that age, no, they don't know. I even heard kids are saying that in cold water, it's faster because in cold water you run, you don't, and in hot you don't move. Kind of thinking about them as an analogy, and it was 6th graders, 7th grader, even 8th graders. So it's about 12 years old to 14. That's the range, middle school. And then we asked them to design a paper model, explain what is going on in those cups. What do you think happened there? We have an amazing paper model and pictures of how do they see this? And then they start working with MoDa. We show them MoDa, we explain to them, we have a very simple introduction to the tool, so they will easily work with it. It's very easy for them. Lots of the kids are doing Scratch. I don't know about here. Do they do in Hong Kong Scratch? So they go very easy to this, and I think it's harder for the teachers. For the kids, it's like, oh, it's like a pen. You give them a pencil, they know how to draw. And then they do a lot of work. Well, they share out their work, they do pair design, and we collect a lot of data. And you can see in bold all the data we collected. So we did pre-test and post-test with open-ended. One of the problem, and I think not a problem, but limitation of the study is that we have data of different types. So we use the same tool to analyze it. I'll show you the tool in a minute, but we have different types. So some of them are drawings, some of them are share outs of videos, some of them are individual model, some of them pair model, and some of them are open-ended question. So it feels like it's a bit of an issue if you look at the different types of data. And you as researcher know what I'm talking about, I'm supposed. So the research question were 2. In what ways do the design activities support students in developing 2 types of learning? We were looking at 2 types. One of them is mechanistic reasoning. Mechanistic reasoning is how does the student talk about the micro level of the phenomena? How do they understand the entities, the interaction between them, the activities between causality and cause and effect of the phenomena? And canonical understanding. This is scientific principle. Do they know the scientific answer? And what does it mean? So we were looking at this, and then we looked at what is the relation between student mechanistic reasoning and their understanding of diffusion. Meaning, is there a connection between they start talking about entities and their scientific understanding of the phenomena? So we were looking at different way to do the data analysis. We actually adapted from Ross et al. And Tina, I don't know if you know Christina, they're working on some mechanistic reasoning, but Ross was one of our main framework that we were looking at. And we have this rubric for mechanistic reasoning about diffusion, which include a lot of codes. We were looking at how they identify entities, how they identify activities, how they identify properties of activities, their organization in space, and causality. Explaining from cause and effect. On the other side, we were looking at canonical understanding. So we were looking, how do they explain diffusion? And we're looking at two different types. Particle interaction, what are the interaction between particle? And what is the impact of temperature on the phenomena? So there's two things that we were curious about, see how children learn. So each data source that you saw before, remember the pictures with a lot of sources, was coded separately to assess student mechanistic reasoning. And we have about 16 students. It was a very small setting of kids. And these are the findings. I'm going to go through 3 only. There's more, but this time I'm going to show you only 3 of the findings. So the first one is that modeling, and we were very excited about it. It's the modeling, and especially working with MoDa, the environment, shifts student explanation from very simple mechanistic reasoning to sophisticated mechanistic reasoning. And let me show you the graph. So you can see the data they work at, and you can see when MoDa was in the picture. And what we see with the beautiful colors is the different component of mechanistic reasoning that we were coding. So we, as I said before, we were looking at entities, properties, activity, causality, and here they are. You can see that they increase. So there was a shift in mechanistic reasoning. And here is one example of one student that was writing in the pretest, I imagine it spread through the water, maybe because of gravity. That's what she was thinking at the beginning. After working with this and doing a lot of things, at the post-it, this was her answer. She said the ink particle bounce off of the water particle. When the water is warm, the particles move faster, so the ink particle moves through the water faster. When the water is cold, the water particle moves slower. So when the ink particle bounce off of them, they move slower. So you can see the difference of these kids and how she really understands what's happening in this phenomena. So that's the first finding. The second finding is that when students use the data to compare model with the data, they shift their explanation from non-canonical, alternative ideas, I call it sometimes, like imaginary ideas, to scientific canonical explanation. And actually, this was very exciting for us because we found that this tool, the MoDa, helps teachers see what is going on in students' brain. And I'll show you some examples. So here you can see the shift from non-canonical to canonical. There's tons of colors, 2 graphs, because one of them is showing only explanation for diffusion through the particle interaction. And we separated because there are 2 different scientific ideas that we would like the kids to know at the end. So the second one was student explanation for diffusion through the effect of temperature. And you can see that they got better. I feel like they got the temperature even earlier on day 2. The blue one is the right answer. So you can see that in day 2, they know, one kid know something about the temperature, but they don't know anything about the interaction between particles. And so that's how you see the increase of understanding of the phenomena with the right answer. But when we look at their code, we were very surprised because we had a limited number of blocks. I told you we are doing domain-specific blocks. There's not so many blocks. Kids came with ideas that we didn't know you could do it with MoDa. So for example, all those, I think there's 6 of idea, but there's more. I just didn't put it there. This is the right explanation, 7, bounce off. But for example, attach model. One kid was saying, oh, I know how this happened. Ink just attach to water molecule, and that's how they spread. So we called it attach model. And look, he made it happen. He just made it with a code. Then we had somebody that was thinking, I think maybe about code, the COVID. So he was thinking, oh, the ink is infecting the water particle. So the color moved to the water and infecting it. And he measured to do it. So we were excited to see that from the blocks, limited blocks that we have, students came up with all those ideas and were thinking how to explain the phenomena. So kind of translating their ideas into code, or the connection between code and understanding, which is very interesting to see here. Yeah. Exactly. Exactly. And I'll show what the teacher was doing. It's a thing. How do you explain? How do you validate this? How do you find out which one is right? It's true. So some of them it's easy to show, and I'll show you the one that is easy. But if you want, I'll show you the other one too. I didn't put it in the slide, but he has some hard question here. Yeah. Okay.
That you show us, the particles in the computational model is only showing the ink particles.
Both. I'll show you again if you want.
Because, I mean, we see the particles moving, but I mean, I don't, maybe they are two colors, so I can't see.
No, I didn't add here. You're talking about this. So I didn't add the ink yet. If I want to add the ink, and I'll show you how to do it, I'm not doing any programming about the temperature and anything. Maybe I can do it later if we have time, but I'm just dragging this here and putting it here, and I'm creating ink. So I want to make it very similar to what is happening in the experiment. So I said on mouse click, create maybe less, a little bit less. And this is something also kids are saying, what's the relation between ink and water? What does it mean, a drop of ink? How many ink particles are in a drop of ink? So they come up with more and more questions, a lot of curiosity raised. It's very nice to see. Okay, so here you will see a different, but I want to share something. So you do this, you see they're moving. And now when I click here, I add ink, but they're not moving. Why they're not moving? I didn't put any behavior for that. Okay, great. Good student here. So so I can do that. I can do another ask and ask ink particle, or I just can say, oh, let's do that because it's easier right now and I don't have so much time to do the programming, and I'm doing this and I kind of run them and I'm trying to put the ink, and let's see what's going on. So now you see their differences. Do you see it? Yeah. That's what you were asking, right? Answer? Yeah. Okay. Yes.
Because my experience is actually about computational thinking. So in Scratch, really, when the orange control button is normally means to loop or something. So I want to know
if we have loops here.
Yeah, I want to see the control button.
Sure. We have, I think maybe you mean this, the if, the condition, right? So you could, we use it. I can use it. I can use it later. So let's use it. You ask so many questions, I have to answer. Okay, so if you want to do this, you can, you just like, and then if else, right? Let's do it, two if else, let's do it properly, right? So when we want to do this, let me see if I can find it here. Let's say when temperature is high, I wanted them to move. How would you like them to move? Higher or slow? What's the speed? High or slow? When it's high? Faster, right? Let's do high. And then let's see this we want to do. Just duplicating, and I have some magic trick here. So if it's medium, let's say that their speed is medium. We're still working on the tool, by the way. It's in development. I just asked the developer not to touch it today. So I hope they're not touching it. I really hope they're not going to. I called Nathan and told him, Nathan, don't touch this today. Today is not a good day to do, to add another unit, okay? So this is like, I set the speed in different type, right? For example, let's see if it's working. Let's hope it's working. Okay, they're going really fast. I'm putting this ink and I can see, and I can put here hot water and see what is going on and see if it's working the same or not, or what is happening. And then I can either slow it down and see what happened in cold water, right? And you can do it again, and you can try different things. And there's also graph, and I didn't talk about the graph yet. Okay, so this is one example of one unit. I mean, we could think about data, tons of data that are here in a connection to relocate to this area, for example, and design a unit for something that you like to do. I was very curious about the COVID, so I designed one for COVID, but you can do others, right? Okay, I'll go back to the result. I want to show you. I know we don't have a lot of time. So this was exactly what you were saying. How would you know? How kids will know that attach is not the right model? So we were kind of, I think one of the main idea here is one, give students the ability to try different things, not tell them it's happening, and also act like scientists and understand what scientists do. But the third thing is about modeling. If you ask kids at that age about a model, you do give them a model and you do an experiment, and the model doesn't work like the experiment, they will believe the model. They think that some scientist, genius scientists did it. I call it credibility of model. They believe that the model is right. They won't think that something is wrong with the model, and they don't even think that you can design more than one model. You can change a model. A model is something you make. So I think this is a very big understanding for students. Like we call it meta modeling, and there's a lot of theory about it. There's people who wrote about it. It's not only me. I'm just using those geniuses to use the meta modeling thing. But this is like, what are the limitations of model? Who can design model? And also the epistemic of science. So science is what is science? We are deciding as scientists what is true, right? How do we know? How do you know that it's bounced off? Maybe it's infected. Maybe it's attached. So a lot of conversation in the classroom are not just about the phenomena, but much higher level. And I think that makes them, the kids think. And I love it because I really see that they're thinking, they don't do. They really think about a lot of stuff that are not even in this level of what we meant to teach them. So yeah, so this isn't one. But the one I wanted to say is this one. So here you see when you now know the code. So when all particles move and interact, if touching the wall, they bounce off. But if they touching any other particle, they attach. This is the attach model that some kids were doing. And if you run the model, you see that they're clumping up into attach. So when they do that and they share it with validate it with the thing, they see that this is not clumping. So you can hear them talk with each other. Something wrong with the model. I don't see any clumps here. What's going on? Maybe we do a different one. So this is for the attach. There's other ways to do the validation for the infect and others, and then we're learning as we go because it's not that simple. Kids are smart, very smart. You have to really think, how do you explain them? What do you do? Okay, and then so the last finding that I want to show and share with you is that student mechanistic reasoning and their understanding of the scientific phenomena develop independently. And this was the surprise to us, because once we put together the data, the orange one, from the mechanistic understanding increasing throughout the day, together with the understanding of diffusion, the concept of principle of scientific understanding of diffusion, and you can see they were not aligned. And we found out that students can talk very, very highly on mechanistic reasoning, explaining with details, very high, with all the ingredients of the rubric, but not on a scientific explanation, on something else, on attachment, for infection, different things. So student mechanistic reasoning and their understanding of scientific phenomena develop independently. And students can use sophisticated understanding even with the wrong scientific idea. And you can see it even here on the day 5, when you see that 14 out of the kids are very high level of mechanistic reasoning, but non-canonical ideas. You see, most of them are blue, light blue, non-canonical idea. Only very few, I think 2, can explain bounce off. And then we came up with this, kind of to summarize, we came up with this matrix. If you can see the yellow one, the yellow axis is simple mechanistic reasoning to sophisticated mechanistic reasoning. And we saw that students shift their explanation from simple to sophisticated when they were using MoDa. So students explore theories to explain the data, and they use sophisticated reasoning sometimes with the wrong scientific idea. And when you look at the blue axis, it's non-canonical versus canonical. So they're actually moving to canonical ideas when they compare into data and talking and sharing their idea with others. And I have just a pick to a paper that we're just writing about the movement or the path or the journey that students are going through when they're moving in this matrix and how they move from different, from non-canonical to canonical, from simple to sophisticated. This is average of the 16 student. And if you look here, you can see there's more different paths. So it might be interesting to see, are there type of student that work differently? What makes them exactly jump from non-canonical to canonical? What makes those move of understanding, which is very learning scientist type of data that we're looking at. So I'm going back to this. Remember the title, which was a little complex at the beginning, and I wanted to ask you if you understand and like, what is this title? So this is the title, and you can go back to it and see if it makes more sense now. Is it clearer now? Yeah. Okay. And thank you. This is just me and my family. That's us. So this is my email if you want to connect, and if you want to ask question, I'll be happy to answer. And I prepared some tryout of MoDa, but I don't think you could do it right now. So I'm not going to be doing this because it's kind of like we have about 10 minutes to do it. So, but if you want, I will be able to, connect on Zoom or connect on. And that's it. Thank you for having me.
Thank you so very much. Thank you, Tamar. It's okay. Either way, yeah. So, any questions? We can also entertain questions from maybe. I can't read the small print.
Let me.
I will read it. I will read it if we got any questions.
Oh, okay.
Yeah, tell us. Yeah.
Not yet.
Sorry. It's more of a reflection in the debate with the question. So I find it fascinating that students make their explanation more sophisticated, although it's not scientifically accurate, according to some scientific standards. I think in Karl Popper's theory, he would call this a post hoc explanation. Well, you are attached to your own hypothesis, right? People don't give up their hypothesis easily. They try to fix it until it's completely broken.
Right.
So it seems that students are going through that. They try to fix it. Oh, it's attached, but now it doesn't replicate our observation, so let's fix it. And they don't reject it immediately. So the question would be like, according to your observation, when would students fix it to a point that they decide, oh, I'm going to just ditch this idea and start off with a new paradigm shift, right? I think that would be like a truly scientific moment of scientific
The aha moment,
right?
for me.
This aha moment.
Yeah.
Did you observe any of this aha moment?
Yeah, so we did. Actually, we have been looking at those moments because this is very interesting to see. And especially because we hear from the teacher how hard it is. Imagine you are a teacher and all of a sudden in the classroom you have 7 ideas to explain this. This is so, that's not easy. You work with teachers, I mean, it's not an easy task. So we're trying to figure out how do we make them understand, how do we go to the right, without telling them, without showing them a movie, showing them the movie of how does it work. We could do that, right? Show them the movie of just like, okay, this is the FUHRMANN guys, this is how it works, that's it. And we find that there are few moments. It's not like a magic trick. It doesn't happen to everyone at the same time. There's different moments, and we're very carefully kind of documenting those moments. So one of them is the data idea that, like, for attachment, it really depends what is their original idea. Maybe because they're young, it's much easier for them to change their idea. Young kids are less attached to their original thinking, and they might be easier to change. But few important moments that I can say is one is the data validation, and even we had one kid that was saying that cold water are heavier than hot water, so that's what makes it sink, and that would make it slow down.
and he went to the lab, and we have a scale, a digital scale, and he was kind of measuring hot water and cold water. So, that's weird, it's the same. What's going to, maybe not, maybe I'll have to change it. So those moments, even if it's not inside the environment, make them think next, about the next step.
Yeah, and I think, yeah, this is a very interesting observation. I think a lot of times, I mean, in the traditional way of learning science, we would be presenting the canonical view,
Yeah.
and then there isn't much space for students to explore alternatives. But what you're doing is you actually let the students to generate their own ideas first. So first of all, they don't only see their own, but they see their peers' sort of reasoning or models. And so all of a sudden, and also, I mean, there is no priority comparatively, right? So I have this, you have that, and he has another one. So they are all quite equitable in terms of authority, right, of those models. And then you can then think about, okay, how can we get confirmation? What would be the kind of evidence? And I think that's actually a very good start. I mean, at least people, I think even understanding what is a model, right? A model is, in a way, an abstraction of why something behaves in a particular way. And so it's, I mean, in science or in any sort of academic discipline.
Right.
So models are extremely important, but a lot of times people don't see models as important at all. They see sorts of applications or facts or say trends to be most important. But in fact, I mean, how do you explain all that? How do you make them all cohere? So I think even understanding, you know, what a model is so important. And of course, then you can also let people, I mean, they can also be exposed to some other people's theories, say, including writings about canonical model. What does that mean? Say, if you show them some writing, and then say, what would that be in terms of creating a model, and how would it work? So I think if we leave the children with more space and more ways to explore, I think that would be fantastic.
Yeah. We feel like it's a really constructionist tool, and that's what I like about it. And I think that's the idea of making something that is not feeding the kids what we want them to know, but let them come up with ideas. Exactly what you say.
Right.
Exactly.
We got a question, some questions from Sylvia.
Our students involved in use. Thank you, Sylvia, by the way. I don't know where she is, but thank you. Are students involved in user design or research? If they, so the first question is, are they involved in the user design and research? We haven't done with this with students yet. Maybe. I think, I feel like it's really hard to design the model. For us to design the blocks is not easy. Imagine you have a phenomena, let's say COVID phenomena, and you have to make blocks for it. What will be the blocks? It's not easy, so we are working really hard, and we actually trying to figure out how do we simplify it, and how do we kind of document our process of thinking of designing those blocks, which is interesting by itself. So no, we don't have end user doing it with us. We have teachers doing it with us. And the second question, I hope I answered, but Sylvia, you can ask another one, follow-up question if I haven't. So feel comfortable to ask.
And you can actually turn on your mic and ask.
Oh,
Yeah.
yeah, go ahead. What's the second one? Thank you. Good idea.
Well, the second one is kind of like
Where
this idea comes from. The model must be created by some genius. So students always trust the model because it was created by previous.
I use the word that, because that's what kids are thinking. I had a lot of experiments before that. I did some work with other pedagogy and called bifocal modeling, when they did design and modeling and data. And whenever we did, for example, we did a ramp and a ball,
and they did the rapid ball. And you know, when you do it in reality, there's so many things that gets wrong, and it doesn't look right, and Newton's law didn't work well because of a lot of things. What can you do? It happens when you work. And so when you kind of compare it to the model is perfect. If you show them a ready-made model over the counter, not the one that they designed, it's usually perfect model. So they usually believe the model, and you can make whatever you want in the model. Even the discrepancy is hard for them to see that the problem is the model. They always think that they are doing something wrong. That's how kids.
Yeah, I mean, scientists are the authority, that's what I said. So you start with, if they know that this is a scientific model, then obviously it sort of prioritizes that model. But yeah.
Yeah, I think somebody was trying to ask something, and you can turn on the mic. Good luck to
Yes.
hear you. Please do.
Yeah, you don't have to type into the chat
Yes.
box.
Yes. Oh yeah.
Can you hear me?
Yes, we do.
Okay, yes, I just have a simple question. It's how this model work with a fair test, the fair test concept in science. And because we know that the fair test is one of the very important way to find out the causal relationship between the variables. But I can see this model, that you introduce, it can even work when fair test is not possible in our reality. Okay, I just want to know more about how it's related to the classical science concept about fair test, and how this model can work even when fair test is not possible in reality.
Mm-hmm. So I'm not sure what fair test. What does it mean, a fair test?
So control variables.
Just a fair test with control, and how? So we haven't done it like this yet. We just been starting this, so we don't have a fair. You have something?
No, yeah, maybe.
Wanna add?
Do you think that? No, I'm just maybe thinking if that has to do with the idea of the epistemology of science that you were mentioning. That science is not, precise, but the idea that the kid can also, like, by using this, by interacting with this, kind of develops this mindset of how science is made. Do you think that kind of?
I'm not sure that's what he means. I'm not sure.
Okay.
It's a good point, but I'm not sure that what
Right.
he actually mean. I'm not sure if I understand what exactly do you ask. Maybe you can write it
Like,
again.
will you build a
Okay,
model
okay.
and
Yeah,
hypothesis to conduct
because
experiment?
actually we have we put the variable together, some what we call the dependent variable. For example, it's not a phenomenon, but we want to explain is the dependent variable, and then of course a lot of independent variables would affect.
Okay, you're thinking about the standard test when you ask what are the kids, what are the independent variable, what are the dependent variable. We haven't done this type of test with kids. I think they're young, they're 6th grade or 7th grade. We didn't ask them those things. And we actually really looked at very openly to see what did they learn. In the question, we asked them about the concept of diffusion, but we haven't asked them specifically about dependent and independent variable. Is that answer your question?
That's fine, because I have an idea, in my mind that if they have this backbone idea in their mind, it may make their mechanistic or their mechanistic explanation closer to the canonical understanding. I just like this idea. Okay, that's fine. Thank you.
Yeah. Okay.
Yeah, that's a very interesting idea.
Yeah.
I mean, so if you have a model, I mean, here is just sort of thinking about how the different entities interact.
Right.
But then we haven't quite identified, I mean, in this work, what are the dependent and what are the independent variables, what are we measuring, and what can change, and what is our primary, so what is our primary hypothesis, right? Yeah, so yeah, that's a wonderful question.
It is a good one. So
Yeah.
think about it a little bit more. Thank you.
Yeah, we got a follow-up by Sophia.
Okay. thank you for answering. I just think we sort of learned from various influences that scientists are the authority. Yeah, what you were saying. So Nancy, I was curious what
What those influences are, given your vantage point.
So you want to know what influences, you mean what influence kids to think that scientists are authority? I think it's so, I feel like kids, like they even think that the teachers is an authority. You don't have to be a scientist to be an authority. Even an older kid is an authority.
Yeah.
So
It's relative.
right, it's relative. So think, I think that kids, I think that's what we're kind of a little bit messing with their brain, because we're telling them, you know what? You could write, you could do your own model, you can design your own ideas. And it makes them very powerful. And I feel like after we do this, we saw the teachers were talking about it. I have a short video with teachers talking about it, so excited about how their class changed and how their students are thinking so much differently now. They don't believe in a lot of stuff and they try to do it themselves and they kind of test everything. I think a lot of critical thinking is happening after this activity.
Right, yeah. We are running out of time.
Yeah, okay.
So thank you all for joining us, and thank you very much for the very, I think, very exciting and interesting discussion. A lot of food for thought after this. And if anyone is interested to follow up, please email Dr. FUHRMANN.
Sure, we'll be
Right.
happy to hear from you, sure.
Yeah. Okay, thank you.
Okay.